Welcome back. In this video, we're going to have a discussion about delta time, and we're going to discuss why it's so important to use delta time, especially when it comes to things that we do each frame. Let's start by defining some terms. Delta time is the time between frames, and a frame is a single image updated to the screen. You see, when you're playing a video game, you're looking at a series of still images displayed to you very rapidly. The frame rate is the number of frames updated per second. You'll often hear the term FPS, which stands for frames per second. Now, you'll also hear the term tick, which is synonymous with frame. If you say you do something every tick, you're doing that thing every frame. Now let's consider that we have an actor and we'd like to move that actor through space. Let's say we'd like the actor to move in the world X direction, and we start the actor off with an X coordinate of 0. Now let's say we'd like that actor to move by 1 centimeter per second. This means that our actor starts off at 0 centimeters at a time of 0 seconds. And after 10 seconds have passed, the actor should now have an X location of 10 centimeters. Now, if we assume that we can update the actor's location once per second, in other words, if our frame rate was 1 FPS or 1 frame per second, this would work based on the assumption that the frame time is constant. In other words, each frame exactly 1 second has passed, giving us a constant delta time of 1 second. Now here we have a graph where the horizontal axis represents time and the vertical axis represents the X coordinate of our actor. So at 0 seconds, when no time has passed yet, it starts off with an X coordinate of 0, and after 1 frame, consisting of a single second, we have now added 1 to our actor's coordinate, and now it has an X coordinate of 1. 1 frame later, another second has passed, and we've added another 1 centimeter to the actor's X coordinate, and now it's at 2. 1 second later, we've added another centimeter, and now the X coordinate is 3. Fast forward to 10 seconds, and the actor has moved a total of 10 centimeters. Now consider the possibility that out of nowhere, suddenly our frame time changes, and now 2 seconds pass between frames. We have a delta time of 2 seconds. Well, in 10 seconds, we will have only updated our actor's location 5 times, and if we're updating our actor's location by adding 1 to it per frame, the actor will only have moved a total of 5 centimeters, which is not what we expected at all. Now for the grim truth. Frame times are not constant. They're sporadic. The more your game strains the computer, the more calculations it must make per frame. And the more calculations means more time must pass. So during periods of high strain in the game, you have larger delta times. And when the computer doesn't have as many calculations to make, you have small delta times, meaning the frames are updated much more rapidly. If we're applying the same amount of movement per frame, this means the character's movement will be sporadic and unpredictable. So if we have our actor and we wish to move the actor at a constant rate of 1 centimeter per second, if we just assumed that each tick a single second has passed and we move the actor by 1 centimeter per second, we'll get sporadic movement. This is the wrong approach. And by the way, frame times are much smaller than 1 second. Oftentimes, games run at 60 frames per second or even 120, which means if you're expecting to move your actor by 1 centimeter per second and your frame rate is 60, you'll actually be moving it by 60 centimeters per second, which is much faster than you expected. What you should do instead is take your desired movement rate and multiply it by delta time. This will scale the movement rate by exactly the amount that you need to move your actor by the desired movement rate. For example, when our delta time changed to 2 seconds, we found that by updating the X location half the number of times, our actor only moved half the distance it needed to move. But if we had moved our actor by 1 times delta time, then delta time being 2 would result in us moving the actor twice as much every frame, and the x-coordinate would have reached 10 by the 10-second mark, as expected. So by scaling our movement rate by delta time, we're scaling it by exactly the amount we need to give our actor a constant movement rate. Mathematically, we're taking our movement rate, which has units of centimeters per second, and we're multiplying by delta time, which has units of seconds per frame. Now, in mathematics, when you have like terms in the numerator and denominator, those terms cancel, and you're left with units of centimeters per frame. Now think about it. How many centimeters do you have to move the actor in a single frame in order to get the desired movement rate of 1 centimeter per second? That amount is the number of centimeters to move per frame. So that gives us the exact amount needed. We're going to put this principle into practice when we move our character in the videos to come. We'll see you back in Unreal Engine.